Hello everyone, welcome to another lecture in distributed networks. In today's lecture, we are going to be focusing on link aggregation and first hop redundancy protocols. So, in the previous week, we have talked about how we can have redundant links when we are building larger networks, expanding into larger enterprise networks. That one of the things that we will do is having redundant networks. And one of the things that we covered in the previous weeks is spanning tree protocols. And the main purpose of spanning tree protocols is avoiding loops that are being created as a result of redundancy links. But doing that, removing redundant links in such a manner can sometimes have a number of disadvantages. And that is what we are trying to address through link aggregation, and then also we'll look at first hop redundancy protocols. So when we look at link aggregation, so when we are aggregating number of links, so say if we are taking these two entities and we have two links, the problem that we would face when we are using spanning tree protocols is one of these links will be disabled or blocked. So then as a result, having that redundancy will only be useful at the point of a failure. Only when the other link fails, this blocked link will become active. All the other times, this link will still be there but not being utilized. But in many network situations, it would be advantageous if we can also use that link. So if we have these two links, if we can use both of those links at the same time, then we can get double the throughput, we can better the performance of the network. But because of spanning tree protocols, because of the need to avoid loops and as a result other consequences that we covered previously, we are blocking these links in spanning tree protocols. So with the main purpose of link aggregation is addressing that issue. Link aggregation will address the issue of blocking links and being able to use those links in a more effective manner to get a better network performance. So the basic idea behind link aggregation is this. So if we have two devices, say we have one device and we have another device, and these two devices are connected using a number of links. So in the case of spanning tree protocols, what may happen is it may go and block the two links and only leave one of the links so that there's no loops happening. With link aggregation, what we are going to do is we are going to combine these links, we are going to combine these three links into a single link. So it will be seen as a single link. So then spanning tree protocols don't have to disable them or disable one of them. So it is a combination of multiple physical links into a single logical link. So we are taking multiple physical links and creating a logical link. Then such group of links that we would call as link aggregation groups or LAGs. So a group of physical links is what we would call as a link aggregation group. Then in addition to this, we may use certain protocols to manage this, such as a link aggregation control protocol, and there are a number of other protocols we will discuss a bit later in today's lecture. But the main idea of link aggregation is this. We take multiple physical links and then we create a single logical link out of it. So then there's no need to disable one or more of those links because now it is a single link, so there's no issue about having loops and as such. There are a number of reasons why we would want to use link aggregation. Because, say, if we have a 100 Mbps link, or if we have two of those links, if we don't do link aggregation, then we are only getting one of these links available to us. The other link will be disabled. So that is quite a lot of wastage of our resources, and also we will be limited in terms of the bandwidth that we can have. So if you want to increase the bandwidth, we are not able to do that here. But if we aggregate these links into a single link, so we can use both of those links and we can double the bandwidth that we get up to 200 Mbps. So we can get increased bandwidth using multiple links. If you want to increase the available using the available speeds, but we double up the links or triple or whatever the number of links, and we can increase the bandwidth as far as we are adding more physical links. So then we can have this increase by simply adding one more link. So if you want to add another link, we can have double up the speed, then triple up, or 4 times. Likewise, we can do that. Another issue or another advantage that we can have is we can have increased availability. So again, because it is an aggregated link, even if a single link fails, the link still is active. So because it is an aggregated link, all of these links will be considered together as a group. So even if one of those links fails, the other one is still active, or other number of links that are there, they are still active. Then we can do load sharing. If you are using aggregated links, again, we can do load sharing and spread the loads through number of these different links in parallel. Then we can do auto configuration. So again, if there are changes in the physical links, if there are changes in the physical connections, because it is still the same logical link, there are no need to change much on the ends of the logical link or anything that uses the logical link. They can still communicate through that logical link. The physical link can be reconfigured automatically. So it can be auto reconfigured, auto configured. And the same thing can be done in terms of rapid configuration, reconfiguration as well. So again, if something changes, again, it can auto configure, auto reconfigure there. So these are some of the goals and some of the things that we want to get by using link aggregation in our networks. Some of the other things that we may want to get out of using link aggregation are, for example, what we call as deterministic behavior. So that is, if we make certain changes, or if there are certain changes that happens, then the changes or the results or effects of that are also something that can be predicted. So because we have aggregated them into logical links, now only the logical links are being used for the communication purposes. So even if things change in the physical link layer, the communication is not affected, the behavior is not affected as a result. And then in terms of duplication or misordering of frames or packets, again, because these are still, again, the sake of using the logical links, because it's still communicating through that part. So even if the underlying physical links are being reconfigured, there are less chance or lower chance of duplication or misordering of frames, because they are still being forwarded through the logical link interfaces. And given that these links are considered as a combination of these physical links, but those physical link layer attributes still exist. So if we are connecting to some devices that don't have link aggregation capabilities, they can still be operated, or they can still function as individual links. So there will be some form of backwards compatibility when we are connecting, or when the devices that we are connecting to don't have any sort of awareness of link aggregation. And certain devices we may set up number of link aggregations. So multi-link aggregations, it's possible to set up, say, number of different link aggregations to few different devices. So that is something that is possible. But the only thing is, each link aggregation group will only communicate between two devices. So a link aggregation group cannot be shared, but one device can have more than one link aggregation with two different devices, so two or more different devices. So when we talk about link aggregation, so the basic idea, the basic thing that happens there is, it is so the MAC address level communication. So because like we are talking about the physical layer communication or the MAC address level communication. So what would happen is all these physical layers or all these physical links that have their own MAC addresses, then those links will be combined into a logical link MAC address. So there will be a separate MAC address that will be assigned to this particular logical link, and the communication will happen using that particular MAC address through the aggregated MAC address. So any MAC address client will communicate through the aggregator. So that aggregator can bind any number of MAC address or ports into that aggregator, and any communication through those ports can go through this aggregated link. So say if we have a number of ports on a device, so these ports can be, so then there will be an aggregator, and a number of these ports can be assigned to an aggregator. And maybe we can have another aggregator assigning a number of other ports. And then all the communication will happen through this aggregator port, or the aggregator will be the part where link aggregation through which all the communication will happen. The only thing to remember is a particular port can only be assigned to a single aggregation. So a given port can only be bind to a single aggregator at a particular point in time, so that a particular MAC client will only be served by a single aggregator at a particular point in time. Then, for example, that aggregation can be removed, and then maybe it may be assigned to a different aggregation at a later point in time, but within a particular point in time, they can only be assigned or bind to a single aggregator. And this management of aggregation, which ports are bind to which aggregators, will be managed by some form of link aggregation control function as part of the system. It could be part of a protocol. Underlying system will have to have that capability to assign these ports to specific aggregators, and then binding and unbinding them as needed. Such binding of ports to link aggregation and all the configurations, all the binding, monitoring, and all these things may be managed through what is called a link aggregation control protocol. So that would be the underlying protocol managing this overall operation of link aggregation. One of the main things that will have to happen is when we are using link aggregation is what we call as frame ordering. So when we say frame ordering, that is, say, if we are receiving different frames at different ports, and then they are forwarded onto the link aggregation, and then it is forwarded through the aggregated link, and then they are received back again at the other end through one of these ports. So here it may go through any of these links. Say, for example, what we may have is, we may have, say, a connection or something being forwarded to the link aggregation. There it can be forwarded through any of these three links to the other end. Then it has to be again received at the other end as a stream of information. So when we are sending frames, we can send frames in parallel using any of these links. So we don't have to pipeline or like stream one after the other through a single link. We can go through any of these links in any order. But what we would expect is when we are receiving at this end, they are received in the same order as they were sent at the beginning. So that type of frame ordering, we would want to ensure that same frame ordering is kept, or that can be ensured, so the receiving end can process the information appropriately. In certain situations, we may use these links or link aggregation for the purpose of load balancing, but in some other situations, we may use this for the purpose of maintaining availability. So these are two different requirements we want to achieve using link aggregation. One is high availability, so even if one of these links fails, the overall link stays up. That is one requirement. The other one is we are using all these links to balance the load through all the available physical links, again getting better utilization of our network resources. So for both of these things, the link aggregation protocol and the link aggregators at both ends will have to cater to those needs. And as I said previously, each of these aggregators, both the aggregators at both ends, will have their own unique MAC address that is different from all the port-specific MAC addresses through which all the communication can happen. So when we look at a link aggregation group, when we have a group of links aggregated together as a link aggregation, when we think about the communication happening in this link aggregation, there are a number of different things will have to happen. The first one is what we call as link distribution. So with link or frame distribution, what happens is all the frames that are being received at the link aggregation will have to be split into the available ports for transmission. So they will have to be appropriately split into the available ports for transmission. Frame collection is on the other end. When these frames are received from different ports, they have to be collected together and forwarded onto the MAC client. So frame distribution will happen at the sending point and frame collection will happen at the receiving point. And in addition to this, we will have what is called the aggregator parser or multiplexers. So these will be again used in terms of again when we are sending these frames using multiple links. So again, how we are going to spread them across these available links, or identifying the appropriate ports to forward these or send these frames through. So again, this is the role of aggregator parsers or multiplexers. Then all of these things together is what we would call as the aggregator. So the frame distribution, frame collection, and aggregator parser and multiplexer together, we would identify these three components as the aggregator. So that is the combination of all these tasks in a link aggregation group. In addition to these, we will also have what is called aggregation control, that is going to manage the configuration, all the control aspects of this link aggregation, so management of the process. And then we will also have control parsers and multiplexers that are going to pass information or pass frames relevant to control entities. So the keeping up of the links, management related information will be passed on, communicated through control passers and multiplexers. So these are also additional information, additional components that will be there as part of a link aggregation group operation. So these may send additional information that are relevant to the management of overall link aggregation. So when we think about link aggregation groups and configuring these link aggregation groups, the main thing to remember is these can be implemented significantly differently from different vendors. For example, Cisco may implement this differently. A different manufacturer of these devices may implement these differently. So this is something that you will have to figure out depending on the nature of the device, depending on the type of the device that you are using, and in terms of referring to the manuals and specifications of those devices, you will be able to identify what is the appropriate approach to configuring these link aggregation groups in such devices. So when we think about link aggregation, now we have already identified there are a number of tasks that needs to be performed for this link aggregation to work, the operations that need to happen, such as distribution, collection, multiplexing, and all these things will have to happen when we are implementing link aggregation. So to specify that or to make that in a standard, there are certain protocols. One such protocol is what we call as the link aggregation control protocol. So this is something that would define and specify what are the information and how specific those information should be, and all these standards will be specified in this particular protocol in terms of establishing link aggregation. In addition to link aggregation control protocol or LACP, there are other proprietary protocols developed by Cisco and many other vendors. They may have their own protocols or own extension to this link aggregation control protocol, and they may function slightly differently, have slightly different features, but in essence all of these protocols will cover the basic operation of establishing a link aggregation and then communicating through that link aggregation, and then maintaining, auto configuring, and all these things will be covered as part of these protocols as well. So if we look at link aggregation control protocol specifically, the main thing to remember is it is an open protocol, is an open standard protocol. So it will be implemented in many different vendors, or many different vendors would implement this particular protocol. It is not a proprietary protocol. And in LACP, when we are implementing LACP for a link aggregation, what we would have is we can have three modes. We can have on mode, active mode, and passive mode. So when we say on mode, that is there's no the protocol is not being used. The link is there, the link is active at both ends, but the protocol is not being used. Then active mode is the link or the port on one end is actively seeking to see if the other device wants to establish a link aggregation. So if the other side wants to establish a link aggregation. Passive is waiting to establish a link aggregation, but it will just wait until some other entity is calling on. So for example, if both entities are on, then a link aggregation can be established even without any negotiation. If one is passive or active and the other one is active, again we can establish a link aggregation. So one should be active and the other could be either active or passive. Other situations, we will not be able to establish a link aggregation channel. Either one is on and the other one is active, one is on and the other one is passive, or both are passive. So all these situations, we will not be able to establish a channel or a link aggregation channel. So then if we think about link aggregation standards that are proprietary to different vendors, then for example, Cisco has what is called Ether channel or port aggregation protocol. So these are two different protocols relevant to link aggregation. Juniper has aggregated Ethernet, ZTE devices has smart groups, Huawei has ETH trunks. So there are different vendors having different types of standards. Many of them will also implement the LACP or link aggregation protocol, control protocol, because it is an open standard implemented by multiple vendors. But in addition to that, these vendors, their devices may implement some of their proprietary protocols as well. Now let's look at Ether channel, which is a Cisco proprietary aggregation standard. So it is specific to Cisco, and Ether channel, in a way, it sort of complements the existing LACP protocol. It's not competing with LACP. It is, in a way, does certain other things in addition to what can be done using LACP. But essentially, it is a link aggregation. It is what it does. Link aggregation is what it does. So there are a number of advantages to using Ether channel for link aggregation if we are using Cisco devices, because this will only be available in Cisco devices. One is the configuration can be done at the Ether channel interface, or at the logical interface. We can do the configuration at the logical interface instead of the individual ports that we have. So the configuration can be slightly easier in some ways comparatively. And then Ether channel will utilize whatever the existing ports that are available on the device. We can use it to get load balancing, and it creates a logical link, as we have seen previously as well. And it can also be used to get redundancy. So the two requirements that we were trying to get out of using link aggregation, both load balancing and redundancy, we can get that using Ether channel. But there are some restrictions when we are using Ether channel. That is, we cannot mix types of interfaces. So that is, if we have, say, fast Ethernet and gigabit Ethernet interfaces, we cannot group them into a single Ether channel. So we cannot combine them into a single Ether channel if there are interfaces of different types. Then in terms of the available bandwidth, there is a limitation in terms of 800 Mbps in a fast Ether channel and 8 gigabits per second on a gigabit Ether channel. And on Cisco IOS, it can support up to 6 Ether channels. Per device, it can support up to 6 Ether channel groups. And it can also, the thing is, it can be created between either two switches or maybe a switch and a server as well. And when we are using VLANs, one thing is, if one side is configured as a trunk, then the other side also must be configured as a trunk within the same native VLAN. So if you recall what we have covered previously about VLANs, both of these things should belong under the same native VLAN. And the other thing is when there are changes to a logical port in the ether channel interface, then that also affects the underlying physical interfaces. Then another Cisco proprietary protocol related to link aggregation is what we call as port aggregation protocol. So port aggregation protocol, again a similar link aggregation protocol. It has three states again here. It has an on state, a desirable, and an auto state. In on state, if both are in on state, a channel can be established without any negotiation. If it is in a desirable state, it is similar to asking or actively asking for the other side to participate, and auto is similar to passively waiting. So when we compare this with LACP, it is fairly similar. So LACP has on, active, and passive, and port aggregation protocol has on, desirable, and auto. Other than that, they are fairly similar in terms of these three modes or these three states. Now let's briefly look at some ways that we can do link aggregation configuration in a device. So if you want to do link aggregation configuration, let's look at some of the things that we'll have to do regarding that. Say for example, if we need to configure ether channel, one of the main things that we need to make sure is both sides have matching settings, because ether channel can only be established between links or ports that are matching speeds and so on. So it has to match at both ends. So to establish ether channel, we'll have to have that. For example, if we have, say, one port is doing half duplex and other port is doing full duplex, then we are not able to establish ether channel. We have to have same speed, same duplex mode, and same VLAN as we discussed. Then when we specifically think about configuring the interfaces for ether channel with LACP, for example, we have to specify the interfaces that are going to be part of the ether channel group. So we have to specify the interface ranges that are going to be part of the ether channel group. So we will configure that range. So the configuration will be done not on a particular specific interface. The configuration will be done on that interface range. There we can create a channel group, and we can specify the mode as active, for example. So it is on an active mode, so it can establish these link aggregation, establish the ether channel, and then we can also change the port channel settings at the interface to configuration mode. Then we will also specify the switch port mode to trunk, and we will also specify the allowed VLANs for that specific trunk. So then we'll have to repeat the configuration at both sides of the interfaces. So we'll create the interfaces or group of interfaces here, and then when both of those are in suitable modes at both ends, then they can establish a ether channel link aggregation. So when we are verifying link aggregation, there are a number of things that we can check. We can check to see the port interfaces as part of a channel. So as part of to see if the port channel is active, if the port channel is connected. So that is the interface is active, that ether channel interface is active, that aggregated link interface is active. We can go and see the summary of ether channel, like the status or the summary of the ether channel, to see again whether that is active, what is the protocol that is being used. Say for example, here it may indicate that it is group 1. The port channel is the protocol, the ports that are participating in that port channel. So these things can be viewed using the show ether channel summary command. Then we can also use the show ether channel port channel command to view all the specifics of the port. So that is the specific ports, the ether channel status of those ports, and all the communication relevant to that. We can again view using these commands. Then if we go into specific interfaces using show interfaces ether channel command, again we can there again see what is the port, what is the state, where the and the LACP port, all these specifics relevant to the ether channel for that specific interface. We can view that as well. One of the main troubles that we may get when we are configuring ether channel is some misconfiguration. Specifically, one of the common things that can happen is when we are having mismatching interfaces. So that is related to the speed of the interfaces, duplex modes, allowed VLANs, allowed native VLANs, and the trunks are assigned to the same VLAN. So these are some of the things that again we can verify using the show ether channel summary command and verifying whether they are assigned appropriately. So we can see if it is in a down state, then we will have to go and check what is if there are any misconfigurations, so that that can be fixed accordingly. Now let's look at first hop redundancy protocols. So the concept of first hop redundancy protocols relates to the need to having a gateway when we are communicating in a switch network. So in any sort of switch network, say let's take this example in this diagram. We have PC1 and PC1 may be connected to a switch. Then at some point it will have to be connected to a router for it to communicate to other networks. So any communication to other networks will have to happen through this router. So that router becomes an essential part of that communication. So then at the switch network level, if we build redundancies, link aggregations and everything, if that is still there, but if for example if this router fails, if the router is no longer available for some reason, if that router fails or the link to the router fails, then this device is no longer able to communicate. So the concept of first hop redundancy protocols is us having a way of redundancy for this gateway. So the gateway will have to have some form of redundancy. So if one fails, we can use the alternative gateway and go. So the default gateway will have to have an alternative option there for the communication to happen. So that is the basic concept behind first hop redundancy protocols. So to achieve this, what we will have to have is a redundancy at the router level. So if we have a particular router that we are connecting to, then we will have to have a redundancy at the router level. And we can implement or we can have this by using the concept of a virtual router. So what we can have is we can have a forwarding router through which all the communication will normally be happening. So that is the default gateway that we have, the default forwarding router. But then what we can alternatively have is we can have an alternative standby router. So the standby router is the backup router or the redundant router that we have. But at the point of configuration, at the point of configuring these devices, these PCs and other devices, other node devices, there we can only set a single default gateway. We can only set a single router as the default gateway. So for that purpose, what we will have is we will have the concept of a virtual router. So this virtual router is what we are going to configure at all of these devices. So they will be connected to the virtual router, or they will be connecting or communicating to the virtual router as the default gateway. Then this virtual router will be implemented in a way that it can be either the forwarding router or the standby router. So it can either be the forwarding router or the standby router. So as long as the forwarding router is actively available, all the traffic will be forwarded to that. But then when the forwarding router fails, then it can go to the standby router. So both of these routers will still be working, and the configuration point, it will only be configured to the virtual router. So the concept of having this level of redundancy, this level of router redundancy, is what we would establish, what we would enable using first hop redundancy protocols. So then the main thing that will have to happen is the way how the virtual router or the forwarding router, the failing of the forwarding router can be detected, and then the traffic can be forwarded onto the standby router, or the standby router taking the active role after a particular point in time. So that is the main task that we will expect from the first hop redundancy protocol. There are a number of ways that this failover can be detected. Say one way this can happen is the standby router. So the standby router will be sending hello messages to the main router, to the forwarding router. So the standby router will be sending occasional hello messages, and then if that hello message is responded, a response is received, acknowledgement is received for the hello message, then the standby router will think still the forwarding router is working. If there is no response received back, then the forwarding router will assume that the standby router will assume that the forwarding router is no longer active, so this is no longer working. So now this is the one that has to do the forwarding. So now it will take the place in terms of the virtual router. So first this will assign itself as the main router. When that fails, the other router will take its place. So it will take the relevant IP address and the MAC address, it will assume those roles, and all the information that is coming through the LAN will be forwarded to that. So that is a way that we can manage the failover when we are using a virtual router and a forwarding and a standby router. So there are a number of first hop redundancy protocols that would establish, or that would enable this function, and a Cisco proprietary protocol for this is called the Hot Standby Router Protocol, or HSRP. It's a Cisco first hop redundancy protocol for IPv4, and then there's the IPv6 variant called HSRP for IPv6. So they both of them have the same functionality of having an active device, a standby device, and a virtual router functionality, and then choosing between those two devices as appropriately. So HSRP is a Cisco proprietary protocol. In addition to that, there is what is called a VRRP, which is the standard protocol or open protocol for the same purpose. In addition to that, there are a number of variants such as gateway load balancing protocol, which is again another Cisco proprietary protocol. Then there is the IPv6 version for gateway load balancing protocol for IPv6. Then there is the non-proprietary open protocol, that is the virtual router redundancy protocol version 2, and version 3 is capable of IPv4 and IPv6. And then there is also a patent-free Cisco protocol, that is common address redundancy protocol, that is a patent-free protocol but still a proprietary protocol. So let's briefly look at how hot standby router protocol functions. So the concept is fairly similar as we discussed previously. So if there are two routers, one of the routers will have to be elected or selected as the active router and the default gateway. So one of the routers will have to be chosen as the active router and the default gateway, and the other router will become the standby device. So this decision between these two will have to be done through the protocol. And then if the active router fails, the other standby router will assume the role of the active router. All the host devices will be configured with the virtual interface. So the host devices will assume this virtual interface as the default gateway that they are communicating to, and both of these devices will take up this information when they take the active router state. So when we have the one active router, that active router will take the role or take the information relevant to the virtual router as its information, and all the communication will happen through that. When that fails, the other device will take that same information, and now all the communication will happen through that other standby router, that is now the active router. But the information that the nodes are communicating to is the information or the gateway information relevant to the virtual interface or the virtual router that they are communicating to. There are a number of slight variations in terms of HSRP as well, version 1 and version 2, and the main difference being version 2 has authentication support, and a number of variations are there between the protocol there. Then within HSRP, deciding which router becomes the active router and which router becomes the standby router will be done using an election process, and this will consider the IP addresses of the numerically highest IP addresses of the router. That router will become the active router, and in addition to that, there can be an HSRP priority set to a router, and then the router can become active router based on that priority. So that is HSRP priority. And then it can also have what is called HSRP preemption, and preemption is about when a router will elect or will trigger a re-election process. So this can happen if there are a number of routers and one router becomes a new router becomes available online, then it can trigger a HSRP preemption to become the active router among all the available routers. So that is about which router becomes the active router, and the other routers will be the standby router using this priority method. Then in terms of the routers and the states of routers, again they can, in terms of HSRP, routers can be in a number of states. The initial state is when they are switched on, then they enter the state for the configuration state, and then they go to the learning state, whether they are router is waiting to hear something from an active router to figure out what is the active router. It has not determined the virtual address or anything like that. Then listening state is router knows the virtual address, but router is still not the active router or the standby router, but it is still listening to the hello messages from other routers. Speaking is when the router is sending out periodic hello messages and actively participating in the election process, become the active or the standby router. Then standby router is the candidate that is going to become the next active router, and active router is the one that is currently chosen as the active one, and this will send out periodic hello messages to all the other routers. Then in terms of configuring HSRP, we'll have to specify the HSRP version. Then we'll have to configure the virtual address for that particular group. Then we can also optionally configure the priority value, and if we need to preempt, then we can also active router to preempt standby using the preempt command as well. So a sample configuration can be as shown here. So we will go into the interface, as usual, configuring the interface, then standby and specifying the version of HSRP, configuring the IP address, priority, preempt, and that way we can configure that. Then once we have configured, we can also verify the standby status, or we can either use the standby brief or the detail command to see whether it is in active mode or whether it is in standby mode. So it will be indicated whether that particular router is in active mode or standby mode depending on the configuration. Then one of the other things that can happen when we are working with HSRP is sometimes we may have certain issues in terms of, say for example, there may be some issues in terms of electing a particular router as the active router, and then there may be conflicts in terms of that. For example, a standby router may lose track of the active router, and then again it may not take the role of active router when there is a failure. So then that may happen sometimes. Then the virtual router and all the routers belonging to that group may be configured incorrectly, and most importantly, the end devices may be configured incorrectly. So the end devices will have to be configured to the specific virtual router, but sometimes if they are accidentally connected to the active router directly, then the advantage of HSRP may not be gained, because they may not switch over to the automatic switchover through the virtual router may not happen for those devices. So that's all that we have to discuss in terms of link aggregation, and then also in terms of first hop redundancy protocols. Both of these are mainly relevant to when we are establishing into larger networks and having redundant links and redundant pathways, and then also having redundant routers. So then we can have higher availability networks, more reliable networks. So these two approaches are mainly about that. So if you have any questions about this, please let me know using our usual communication methods, and there will be some activities relevant to this that is available on the LMS as well. And as always, please attend to those on time. And until next time, thank you for joining in this lecture. See you next time.